Hello, everyone. I think it's going to be a fairly quick section in this video. We're doing section 16.4, which is Green's theorem. Now this, if you're just reading it on your own, could be kind of intimidating, this section. I'm going to present it in a way that will hopefully make it a bit more comfortable for you guys, all right? And the problem with Green's theorem, and you will see this if you look at the textbook, there's not a lot of like intuition that they give before they just kind of slap this theorem at you. They give you the theorem, then they give you the proof, and okay, it can be a little hard to digest, okay? But let's just kind of look at it and then discuss it. And we're not going to worry about the proof too much. Just think of this as a tool, okay? So this Green's theorem is going to be a tool for calculating line integrals and relating them to double integrals. Basically, what it is, it's a way to convert a line integral to a double integral and vice versa. So then if we have a problem with a line integral, we could, and maybe it's a little difficult to calculate, we could just switch it over to a double integral and then calculate it, and it would probably be easier. Okay, so let's look at the statement of Green's theorem. My iPad keeps adding these weird, like they're links. That's weird. Okay, I must be clicking something. All right, so this is the statement of Green's theorem. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be a region bounded by C. If P and Q have continuous partial derivatives on a region that contains D, then the integral, this line integral along C is equal to this double integral on the region D. Okay, so this was like a huge wall of text, and probably, even if you kind of looked at it and read it for a while, maybe it doesn't make a lot of sense. So let's kind of do a little quick explanation. Okay, let's go just piece by piece. So we have, okay, this first sentence is kind of a doozy. All right, C is a positively oriented, piecewise smooth, simple closed curve in the plane, and D is the region bounded by C. All right. What does this positively oriented, piecewise smooth, simple closed curve mean? Okay, basically we have just a closed curve, meaning it's a curve that loops back in on itself, and the starting, if I have a starting point, the starting point is the same as the end point. Okay, so let's say I start my curve here. Okay, positively oriented means I'm going counterclockwise. Okay, and then I loop back to my starting point. Okay, and it's a simple curve, meaning I don't have any of these weird like figure eights or anything like that. It's just a simple closed curve. Okay, it doesn't have any weird kind of kinks, and there's no holes in it, nothing like that. Okay, so I think it should be fairly intuitive what that means. Piecewise smooth meaning just like, okay, this curve could be made up of a couple of chunks, but in the end, it like maybe this is a line segment, this is a different line segment. Okay, maybe then we have like a bit of a curve here. Okay, that's fine. It can be made up of these kind of different chunks as long as it loops back on it to its starting point, and it doesn't have any of these weird like figure eights or holes in there. Okay. All right. So that's what C is. And then we're saying D is the stuff inside C. Okay, so C is the yellow curve, and then D is the green shaded region. All right, so that's the first sentence. Now, that's just kind of set up. Okay, now we have, we're talking about a vector field, right? We have P and Q. So we have this, this line integral of a vector field. And what do we know? We know that these components of our vector field have continuous partial derivatives. Okay. Now remember what, for those of you who kind of forgotten what P and Q are, remember we talked about vector fields, right? Stuff like this. f, r2 to r2. Okay, so it takes a point in R2 and maps it to it takes a vector in R2 and maps it to a vector in R2. So the output, so we could write f like this. So f kind of looks like this. The output of f is a vector, and the first component is this function p, second component is this function q. Okay, so that's what these p and q are. Okay, and then what do we know about p and q? They're differentiable. They have first order partial derivatives. They have continuous partial derivatives. And then what does it mean on a region that contains D? Okay, well, that's not too important. It just means like, okay, our P and Q are differentiable on this larger region. So it's not going to be a problem if we differentiate on that smaller region. Okay, kind of a technical requirement. Okay. All right. So that's all, that's more setup. Then what's the meat of Green's theorem? The meat of it is saying, okay, if we take this line integral of our vector field on this curve C, okay, so if we take the line integral on this outside curve C, this outer curve C, that's going to be the same as taking this double integral on the green region D. Okay. So we see in some way the integral along the edge is related to the integral along of the interior region. Okay. Okay. Now notice these integrands, the stuff inside the integrals is not quite the same, right? So if we want to convert, if we were converting this way, we have to do some differentiation. Okay, and then this is basically just what I just said. So you have a vector field F defined on the region. Then this vector field along the outside edge is equal to, assuming this line integral along the outside edge is equal to this double integral along the inner region. Okay, the proof is pretty complicated, and even the book only gives kind of a special case. So we're not going to worry about the proof. Okay, so just think of this as a tool. You can look at the proof if you want. I'm not going to try and clutter your minds with it here. The significance is not to be understated. All right, so let's say we have a line integral. Let's say we have a line integral of a vector field along a closed curve. All right, so this is only working on closed curves where we have the curve loops back to itself. Okay, and let's say I want to calculate this line, the line integral on that closed curve, but for some reason or another, this is a really difficult line integral. Okay, so what can I do? I can use Green's theorem to convert that line integral to this double integral. And the hope is that the double integral will be much easier to solve. Then I just solve the relatively easy double integral and I'm done. And it does work in the opposite direction as well. If I have a difficult double integral, I can convert it to a line integral, but that takes a little bit of finesse. We'll talk about it, but the main application is going to be this direction. And luckily, it's the easier direction. All right. A quick note, we have maybe some of you have already spotted this. We're talking about line integrals on these closed curves, right? So line integrals on curves that look like this. Now, if our vector field F is conservative, what do we know about this line integral? It's going to be 0, right? So that's not very interesting. It wouldn't be very interesting if, we just always have 0 there. So for most of these problems, we're going to see f is not going to be conservative. I'll say for most of these problems, because every now and then you'll come across one where you convert it and it's 0, and so maybe you're working with a conservative vector field. Okay. All right. So let's talk about converting from a vector field, a line integral, to a double integral, and this is the easier direction. Okay. Quick note on notation: you might see the integral of these. You might see the integral symbol for these line integrals with this kind of loop in there. This loop is just meaning, okay, we're integrating on a closed curve, something that circles back to itself. And sometimes you'll even see it with an arrow, kind of arrow pointing counterclockwise, meaning it's positively oriented, where when we're moving around this curve, we're going counterclockwise. Okay, so you might see either of those. Don't be thrown by that. This is still just a line integral. All right, so let's take this line integral and convert it to a double integral. Okay, now this and the c we're given, the curve we're given, is the circle with center at the origin, radius 4. Now this line integral would probably be pretty easy to calculate as a line integral, but let's go ahead and convert it anyway, just to practice conversion. Okay. So first, when I'm looking at my line integral, I need to figure out what's my p and what's my q, right? Well, my p is always the stuff on my dx, and my q is always the stuff on my dy. Now, one thing to look out for is there's a negative sign here, so that's part of your q. Okay. So my p in this case is just y. And q is equal to negative x. Now, what is my formula? Part of this is just memorizing the formula. When I convert, my p, well, let's see, my conversion is dou q over dou x minus dou p over dou y. Okay, so let's figure out what those are first of all. What's dou p over dou y? Well, that's 1. What's dou q over dou x? That's negative 1. Okay. And then when I convert, what is my formula? Let's not worry about the region quite yet. When we convert to dou q over dou x minus dou p over dou y, right? All right, so what do I want for my problem here? I want negative 1 minus 1, right? So that, and this simplifies it, just negative 2. So my integral is just the integral of a constant, negative 2. Now, the only thing I left to take care of is I need to set this region up. I need to set up, I need to set up my bounds and my differentials here. Okay, so let's go back to the beginning. What's the region I'm integrating on? Well, this is the outside of the region, right? This is the curve, and I want to integrate everything inside. So I'm looking at the stuff inside this. Okay, so really I'm just looking at the region bounded by this circle. Okay, so how could I write those bounds? Well, this is going to be a case where, I could do this in Cartesian coordinates, but think about circles. How did we learn to integrate circles? That's nice and easy. Polar coordinates, right? So I'm going to write this integral in polar coordinates, which means I'm going to have a r dr d theta here. And then what would my bounds be? The the circle, we're told, has radius 4. So my r is going to go from 0 to 4. And then my theta is going to go from 0 to 2 pi. Okay. Let's pull our -2 outside. Then we're integrating this. Okay. R squared over 2 from 4 to 0. What is that? Well, that's what? 16 over 2. That's 8. Okay. And I can pull, let's see, so that's the integral of 0 to 2 pi, -2 out front, 8 d theta. Should be -32 pi. Okay, so not bad. Now let's see, let's do one more example. I'll do maybe 1 or 2 at the end as well. Okay, now let's try this. Again, just using the same technique, I'm converting from, I want to convert from this line integral to a double integral. Okay. Well, let's see. Again, I want to figure out, first step, figure out what my p and q are, right? So p is my stuff on my dx, q is my stuff on my dy. Okay. All right, what does my formula ask for? I want dou p over dou y, right? So that would just be x. What's dou q over dou x? That'd be 2x y cubed. And then when I convert my integral, it's going to become this minus this. So I end up with 2x y cubed minus x dA. Okay, so that's what I'm integrating. Now let's set up our double integral, right? All right, so we're told we're integrating, we want to, this is our curve C, so we want to integrate inside C. Let's draw C real quick. It's a triangle with those vertices. So let's see, 0, 0, 1, 0, and then 1, 2. All right, so I want to integrate on this region. Well, we can just integrate in Cartesian coordinates. How do I do that? Let's see, I'm going to pick one direction to be my constants. How about my x's will be my constants? So I integrate from 0 to 1 for my x's. And then what are my y's? What are my y bounds? Okay, well, I'm taking cross sections along my x-axis. Okay, well, the lower bound is 0, obviously. What's the upper bound? It's this line here. Well, what is the line? It's the line between 0, 0 and 1, 2. So that would be the line y equals 2x. Okay. So my upper bound for y would be 2x. Okay. Now all that's left is to integrate. Okay, so let's see, I get 2x y to the 4th over 4 minus xy, 2x to 0. Okay, let's see, when I plug in 2x to y, I get, let's see, 2x to the 4th would be 16x to the 4th over 4 minus x times 2x. And then when I plug in 0, everything's 0. Okay, simplifying. Okay, 32 over 4, that just becomes 8. So I have this integral integrating in terms of x. Let's see, 8/6 minus 2/3. That should just be 4/6. And this, I took this from the book. Let's make sure I'm on the right page. I'm doing things correctly. Okay, this is number 3 from the book. 4/6, which is equal to 2/3. Correct. All right. So that's how you convert from a line integral to a double integral. We can also go in the opposite direction. It, as I said before, it takes a bit more finesse, a bit more difficult. I'll show this for completeness. I don't anticipate giving you a question like this on the final, or I don't know if you'll see it on WebAssign or not. I'll have to look at that, but I'll show you just for completeness. Okay. It's going to be a bit more difficult because we're going to be given this, and we're not going to be told what P and Q are, right? Okay, so figuring out P and Q from the derivatives, that could be a little, a little weird. But the nice thing is, okay, maybe there are a lot of possibilities for vector fields that have these derivatives. The good news is I could use any one of them that works. Okay, and just for context, we're going to usually see these types of problems when talking about area. We're usually going to have a problem like this. Find the area enclosed by the ellipse. X squared over a squared plus y squared over b squared equals 1. And this is exactly the example they give you in the textbook, example 3. Okay, so the work in here is, this is just what the textbook has given us as well. I didn't even see any problems like this in the hard copy of the book. I didn't see any problems like this. No, there are a couple, but the textbook seems to favor the other direction of problem, converting line integral to double integral, and I agree. That's a nicer direction. But let's look at this direction. All right, so I want to find the area enclosed by this ellipse. All right, well, let's leave it as, D right now. So what am I integrating? I'm integrating on some region. I'm integrating on the region enclosed by the ellipse. What am I integrating? When I'm looking for area, I just integrate the number 1, right? Okay, so I'm integrating the number 1. Now this could be a difficult double integral. Finding the bounds of this region could be weird. So maybe we should convert to a line integral. Okay, so when I convert to a line integral, okay, I'm looking at this number 1. I'm saying, okay, this number 1 is my dou q over dou x minus dou p over dou y. So I want to find P and Q such that their partials, the difference of their partials here is equal to the number 1. Okay. So there's a bunch of ways you could do this. What does the textbook say? What ones do they use? They use, okay, they're going to say P is X and Q is negative Y. Okay. And actually what they're going to do is 1/2 X, 1/2 negative Y. Okay. Why do they choose these? Well, we could have chosen a lot of different ones, but when we do oh, and this is reversed. This is so this is what they choose. So why did we choose these? Well, when we differentiate this, when I do dou p over dou y, what do I get? I get 1/2. And then when I do dou q over dou x, what do I get? And the negative should be over here. What do I get? I get 1/2. Okay. So then when I do dou q over dou x minus dou p over dou y, I get 1/2 minus the negative 1/2, which is equal to the one that I wanted in my double integral, right? All right. So that means these p and q work out nicely. Okay. So these are the p and q I'm going to use for my vector field. So let's set up our line integral. It looks like this, right? And we've determined that we're going to use the p equal to negative 1/2 y. And then q is going to be what? 1/2 x. Okay. All right. And then what do we need? We need to compute this line integral. So first thing we need to do is we need what's our c? Our c is that ellipse, right? X squared over a squared plus y squared over b squared. We need a parameterization for that ellipse, right? Okay, so we need an RT, a parameterization for that ellipse. Well, it turns out that it has a parameterization a times cosine of t, b sine of t. Okay. All right, and then I also want to find r prime of t, right? Okay, and then when I'm taking the line integral of my vector field, remember what this p dx plus q dy notation stands for. It's the same thing as this, f dot dr, which is what? F dot product r prime of t dt, right? So when I'm computing this line integral, I have to convert my x's and y's to these things, okay? So what does my p and q become? My p negative 1/2 y becomes negative 1/2 b sine of t. What does my q become? Q is 1/2 x, right? So q becomes 1/2 a cosine of t. Okay. And then I do I can think of this as pq dot r prime of t dt. Okay, so what is that? Okay, it'd be negative 1/2 b sine of t times negative a sine of t plus 1/2 a cosine of t times b cosine of t dt. Okay, simplifying that. So yeah, I got negative 1/2 ab, no, the negatives cancel. 1/2 AB sine squared of t plus 1/2 AB cosine squared of t dt. So let's see, a squared plus, or excuse me, sine squared plus cosine squared is 1. All right. I factor out the 1/2 AB on both terms, so I get 1/2 AB sine squared t plus cosine squared t dt. 1/2 AB dt. So I integrate along my curve. Okay. Well, let's see. What are the starting point, ending point for our ellipse? 0 and 2 pi to go all the way around. Okay. So 1/2 AB. There's no t's in here, so when I integrate in terms of t, it just becomes 1/2 AB times 2 pi. So that becomes pi AB. Okay. Now this was a general, in normal circumstances, A and B would be constants, right? They would be numbers. A and B just showing in general how it works. All right. Again, this is an example of going from the double integral to the vector field, less common. Okay. So I'll check to see if WebAssign has any of those, but I don't believe so. But let's go back. Let's do one more of the other direction. Let's do one more of vector field, or excuse me, line integral to double integral. Okay. So this is back to the easier direction. Okay. So we have y e to the x dx plus 2 e to the x dy, where C, our curve, is the rectangle with these vertices. Okay. So first of all, what's our P? That's our P. What's our Q? That's our Q. So P equals y e to the x. Q equals 2 e to the x. What's our dou P over dou y? It's e to the x. What's dou Q over dou x? 2 e to the x. So dou Q over dou x minus dou P over dou y is equal to 2 e to the x minus e to the x, which is just equal to e to the x. Okay, so my double integral becomes e to the x dA. Okay, now I need to set up my region that I'm integrating on. Well, the curve we're talking about is a rectangle, so this should give me a nice rectangular region to integrate over. Let's draw our region. It's the rectangle with vertices 0, 0, 3, 0, 3, 4, 0, 4. Okay. So if I'm integrating on this, what are my bounds? They're nice and easy. They're nice and rectangular. I could integrate this in either order. So dx 0 to 3, dy 0 to 4. Okay. Fairly straightforward. So integrating in terms of x first, we get e to the third minus 1. And then integrating in terms of y, we get what? 4, just 4 times that. Okay. So that should be our answer. And let's see, did I take this problem from the textbook? I believe I did. The question is, which problem was it? There it is, number 5. Yep, we're all good. All right, so in summation, this is just a tool. for this Green's theorem is just a tool for calculating line integrals and maybe double integrals, right? It gives us this ability to switch back and forth. Okay, so if we're having a difficult time doing this line integral, as long as it's like a line integral of a closed curve, we can convert it to a double integral, and vice versa. If we're integrating on this, if we're doing a double integral and it's kind of difficult, and it has a nice kind of outer edge that we can find a parameterization for, we can convert it to a line integral. Okay. Now, the easiest direction to do is this direction where we convert the line integral to a double integral. Okay, and this is what you'll most commonly see and what you can expect to see on the final, if anything, from this section. Okay, so enjoy, I guess.